Okay, it appears that we are live. If someone can give me a wave or a hello on the chat here, then I know we're good to go. It looks okay. It looks like I'm live. Everything seems to be going well. Just a wave on the chat, then we can get started. Okay, that looks good. Okay, I think we're live. We'll just give it a couple more seconds, see if there's anybody else that's going to be tuning in for today's Earth Live lesson. Okay, everything looks good to go on my end. Okay, I think I'll begin. Hi, everyone. There we go. Okay, we've got hellos, a few more hellos. Hi, everyone. My name's Sam Mitchell. I'm a volcanologist in the UK. Welcome to Field. We've got people doing research in all that looked at anything just yet, loads. Tune into future ones. But for today, I'm going to be talking to you about volcanoes, and in particular, certain things about volcanoes that I find particularly fascinating and that are just really, really cool because, let's face it, volcanoes can be really, really cool. They're very hot, so very, very cool. Okay, I'm saying someone's got some connection issues. Okay, is that going to be an issue? It looks like maybe it's a bit jump and starts. Let's see. Okay, well, I'll keep going for the time being. This is being recorded anyway, so if there are any issues, then hopefully the main recording will pick up all that are being missed within this live stream. So today I'm going to take you to volcanoes in really weird and wonderful places, because we find volcanoes all over the world and we see them frequently on the news. But there are volcanoes that we don't hear a lot about sometimes in the news because they don't affect people as much, but they're just as fascinating to study, and we can actually learn a lot more about certain volcanoes that may be hazardous by looking at volcanoes in other places that may be a bit remote. Oh. So the first place I'm going to take you is to the very, very bottom of the oceans to look at volcanoes. Now, volcanoes in the bottom of the ocean are what I personally study with my research. It's a really, really fascinating area to go into. And if you didn't know this already, there are actually more volcanoes at the bottom of the oceans than there are actually on land, even though we don't see them. Sometimes we can see them erupting at the surface, but sometimes they're so deep that we don't see them at all. So it's a really, really great place. So these images that I'm going to show on the slides may be a little bit washed out, but hopefully you can still get the general idea of what I'm going to show you today. So the Earth's surface is covered by 2/3 of oceans. And so within these locations, there are many places, Sandwich Islands or the Caribbean, or over just volcanoes at the bottom of the ocean in a variety of settings. Really, really fascinating places to go. And compared to the number of volcanoes on land, even though there are many more at the bottom of the ocean, we still have documented very, very few of them because it's very difficult to monitor these kinds of volcanoes, particularly because of how remote they are. They're in the middle of the oceans, they're deep down, they're blocked out by a huge column of water, so it's really difficult to monitor some of these volcanoes. In the past few decades, we've gotten a lot better at this with more frequent expeditions, better technology, better satellite capabilities. So we're in a really exciting time to be studying volcanoes at the bottom of the ocean right now. So you can see this is a picture from an island in Tonga in 2000, because we can visually see them in real time to be able to learn more about them. But sometimes they occur right at the very bottom of the ocean, many, many miles or kilometers down, and they don't breach the surface. So to get to these places, we have to use submersibles. So these are basically submarines. They can be remotely controlled, called ROVs. They can be operated by humans. Sometimes you see them in programs where people are inside the submarines going down. And they can also be autonomously controlled. So we tell them where to go, and then they will go and survey that area. So these are a couple of images that were taken from a volcano called West Marta, around a mile, around just over a kilometer deep. Really, really fascinating place to go and study these deep volcanoes. And so to do these kinds of expeditions, we go out, as a picture from here from a cruise I went on last year. We went out for 5 weeks surveying a volcano off the west coast of the US called Axial Volcano. And so there was a team of scientists, a team of marine technical specialists, team of protected species observers, the crew, technicians, a whole array of people has to come together on these expeditions to make the science worthwhile. So it's a real team effort to go on these kinds of expeditions, but it's also a fantastic opportunity to learn about some of the remotest places on our planet. And there's other things that we can see at the bottom of the ocean. Over here, some of you that are more wildlife related may be able to tell me the exact genus or species of this, but that is some form of squid. It was deep purple, and we found this around a mile down on an expedition harbored around. So they're really these places where chemistry, physics, geology, and biology all cross over. So there's something for everyone in there. And the picture just on the top left here is employing one of these submersibles off the side of the research vessel. So now I've talked to you about submarine volcanoes. We're going to move on to something else, which is glaciers and volcanoes beneath glaciers, so subglacial volcanoes. And just an example here, I think it's reverse for you all, so that does say glaciers of Iceland. This is a picture of a map of the country of Iceland, and you can see the large white patches, which are these large glacial ice caps that sit on top of the island itself. And there are actually volcanoes beneath these glaciers. So before we move on to this, I want to bring in a couple of concepts that are really, really important when studying volcanoes. And the main one of these is pressure. Now, to demonstrate this, I've got our classic fizzy liquid. And I'm sure everybody knows when you shake this up and you take the cap off, we all know what's going to happen. Now, this is fairly pressurized, so I'm not going to take this off. But when I shake this up at the moment, there's not many bubbles that are coming out of this. So they're dissolved within this bottle of Coca-Cola. Can't actually come out until I release this pressure because it's been sealed under a higher pressure. So when I release this, the high pressure system within here wants to drive gases out of the liquid, out through the top into the low pressure atmosphere around. And that's a very basic way to understand volcanoes. You have a high pressure system deep down where these gases are dissolved at depth, and then they erupt out because they're being driven from an area of high pressure to low pressure. So that's the basic there. I will not be opening this. So now that you've got a bit more of an idea of how pressure relates to volcanoes and how it causes things to possibly erupt, we have to know the higher the pressure the volcano. Okay, I'm having a few people saying that it's a bit frozen. Hopefully, hopefully we can fix this afterwards. I'll just keep going for the time being. So as I was saying about pressure, the deeper you go down the oceans, the higher the pressure gets. And so this really affects the type of volcanoes, the eruptive style, how much is erupted into the ocean column. But it's a really fascinating and relatively new area for us to really, really delve into. Detailed modeling, observations. So that is exactly why we want to study volcanoes in these places. So I just want to show you a picture now of a volcano called Grunsvodden on Iceland. And the whole volcano itself sits under a really, really thick ice cap. And so it has to overcome this pressure of the overlying ice before it can erupt out. Now, a really interesting concept is looking further back in time when we think about ice ages. Now, we know for a fact that glaciers have, or they can thin as well. So you're changing the pressure environment above these volcanoes. And so there's really interesting questions being asked in that area of science at how these fluctuations in pressure over long periods of time actually might be able to change the style of volcanism, the type of eruptions. So that's another really fascinating place to think about ice in relation to volcanoes. Now, these images might get a little bit washed out. So I found out if I duck my head out, you might be able to see them a bit better. So we'll see that actually works. That really, really give a good idea of what volcano structures might look like underneath ice caps to the solar system. So for those of you who might be able to guess, this one, obviously we know is home, this is Earth, but this is the planet Venus. Now I've chosen Venus first because they're two planets of fairly comparable size, which means they've got a relatively similar gravity. The gravity on Venus is a little bit less than that on Earth. But the big difference between Earth and Venus is their atmospheres. So Earth has this atmosphere which is rich in nitrogen and oxygen, whereas Venus has this really, really thick atmosphere that is primarily carbon dioxide. And so what we know about carbon dioxide is that it's a greenhouse gas, and this means it traps the heat that comes from the sun inside the planet and inside the atmosphere. So it means that the atmosphere of Venus, one, is very, very warm, and also because of the thickness and how it is, it's a really high pressure system. And so this is really, really great for applying our knowledge of volcanoes in the ocean and volcanoes under glaciers to a higher pressure, exact same pressure that you would feel if you stood on the surface of Venus. So that's 90 times the pressure that we feel right now. You don't feel like you're under pressure when you're standing on the surface of the Earth, but if you were to stand on the surface of Venus, it would feel as if you had 900 meters of water above you. And that's just amazing, I think. Another really different thing about Venus as well, as I said just then, is the temperature of the atmosphere. So these are a couple of images I've put up now of lava flows on Hawaii, the Kilauea volcano from a few years ago. Now, we've all seen videos and pictures of lava flows where it's red, it's hot, and where it's black, it's so that's what happens when lava interacts with the atmosphere. It flows, it begins to cool as it's cooled by the surrounding atmosphere, and eventually this molten lava will solidify and will turn into glass and crystals and then become the lava fields that we see today around volcanoes. And so the cooling process of lava is really, really controlled by the atmosphere itself, and particularly the temperature of the atmosphere. So on somewhere like Venus, where the atmosphere is really, really hot, the cooling process is completely different. So even though these two planets might be comparable in terms of their chemistry, in terms of the gravity of the planet itself, there's big differences in the pressure of the atmosphere and the temperature of that surrounding atmosphere. So those are really two interesting systems. Next upon the list, a little bit further from home. So this is Earth versus Mars. Now, Mars is slightly smaller. So we move away from pressure just for a second, and we bring in another concept, which is gravity. So I've got my apple here for representing gravity. So the simple process by which things come down. And anything that has mass and anything that has size has gravity. So Earth, for example, has a larger gravity than Mars because it's a lot lower than it is on Earth. We've seen those videos where people are jumping on the moon. So if gravity really controls not only how things come down, but how things go up. So an example of that, enough you'll see, you can see this bubble of air trapped at the bottom of this bottle of corn syrup, and it rises to the top. And that's essentially how bubbles rise in magma as well. And that's controlled by gravity. So as well as things coming down, gravity is also responsible for how quickly things move up. And so that's one of the biggest differences when we look at volcanism on Mars, because the gravity is so different. It's also a very low pressure environment on Mars because the atmosphere is really, really thin. So we've got two properties changed there. We've got the gravity changing, we've got the pressure changing, and also it's very, very cold. So the temperature of the atmosphere is also changing. So we've got all these different properties that control the different styles of volcanism that happen over the solar system. But on Mars, Mars has the biggest volcanoes of anywhere in the solar system. And what we've got here, if I maybe jump out, it clears it a little better. Some of the main volcanoes on Mars is a volcano called Olympus Mons. Now, just to give you an idea of the size of this volcano, in terms of its base, it's the size of France, and its height is almost 3 times the height of Mount Everest. Just to give you another comparison, it's about the top of the volcano is around twice the height that commercial airliners usually fly at when at their maximum altitude. So this is a big volcano. So there's a lot of questions as to how these properties like gravity, pressure, and temperature, again, control how the styles and types of volcanoes vary across the solar system. Okay, so we've only got a few more minutes, so I'm just going to hit you with 2 more systems before we wrap up, and then I'll look at some of the questions you might have been asking over the past 15 minutes or so. So the next one, we move away from our close neighbors, rocky planets, and we're looking at Earth versus Io. So we've got planet Earth here, we've got our moon, which is also a very similar size to one of the moons of Jupiter, and Io. So Io is the most volcanically active body in our solar system. As you can see, it's relatively small compared. You might be able to see scattered over the surface of Io are all volcanoes. But Io is so small and has no atmosphere, so the eruptions it can produce are huge, and they can spew material hundreds of miles into the atmosphere. And we've actually seen that, despite the fact that this planetary body is so far, or sorry, this terrestrial body is so far away. We've actually seen volcanic eruptions on Io from the satellites that have gone out there to image these volcanoes. So it might be a little slow, but it's erupting hundreds of miles high into space. And that is just incredible that we can literally see these eruptions from so far away. So that's Io. I would encourage you to look at this. It's also got a really strange makeup, because as you go further away in planets in the solar system, everything starts to change, what the planets are physically made of. And that's what brings our final volcanic system that I'm going to talk about today to a real climax of just how weird volcanoes can get across the solar system. And that is this tiny little body here, which is one of the moons of Saturn, Enceladus. Now, Enceladus is a fascinating place, and it's one of the most interesting places that a lot of our planetary scientists are interested in right now. And that is because it has a liquid ocean beneath a thick shell of ice. So as we know, our planets do vary. Our planet itself has a thin crust, a mantle, and then a liquid and then a solid in a core. But as you go to these smaller moons, they also be. So the moon of Enceladus has a rocky core, a very thick ice shell, but then it also, between those two layers, has a liquid ocean of water. It's at that perfect pressure and temperature where liquid water can exist in a subglacial ocean. And in this case, you think, well, how is this a volcanic system if it's purely just made up of water and ice? Well, what you might be able to see on this part of the planet, if I maybe duck away slightly, okay, it's not really cleared up, are these stripes. Now, these are called the tiger stripes of Enceladus, and they're around the South Pole. And they're these regions where the liquid ocean is actually able to breach the surface. And when Cassini was imaging Enceladus over the past decade or so, it's actually identified geysers, eruptive plumes from the surface of the moon itself. So despite how small this moon is, how small the gravity must be, there is no atmosphere, and it's a liquid ocean erupting out of ice. This is technically a volcanic system. These geysers are erupting out of the bottom of the moon, and this is an area that we call cryovolcanism, and that's just an amazing term anyway. So as I said, we'll give you a bit of a diagram here, so you can see a slice through the moon of Enceladus. You can see big rocky core, this thin liquid ocean of water, and then this thick ice shell, and you can see these eruptions out of the south. That's the final one I wanted to take you through today. Elsewhere across the solar system, so we volcanoes under Glacial, because we think this might be one of the best places to look for life outside of our planet, that they're erupting out of these plumes. Sorry, a second, something just popped up, so I'll close that down. Well, this is streaming to you all. So, what is the most interesting thing you have learned about volcanoes? Honestly, I think all the stuff that I've talked about here is probably some of the most interesting stuff that I've learned, particularly how these different factors of pressure, gravity, temperature, how they affect the types of volcanic systems we see on our planet and elsewhere. What else? Why volcanoes are covered with ice despite being so hot? So the two are quite separate. So the volcanoes actually melt the bottom of the ice cap. So you then have a system of ice, water, and then the volcano itself. So, but if it's a very powerful eruption, then the volcano has the potential to melt the ice in the region above it, which then slumps down and the volcano erupts out of the glacier itself. But the volcanoes can sit dormant for a very, very long time and actually have no change on the ice cap over them. What else have we got on here? Favorite volcano to study? Well, the pressure environment changes. For every volcano, the deeper you go, the different the conditions are. most volcanoes on the surface of the surface of land erupt into pressure conditions that are relatively similar, because the atmospheric pressure that we experience by standing on the surface of the planet doesn't vary so much. However, the deeper you go in the ocean, you can change from a very shallow eruption with very little pressure to an eruption maybe 5 kilometers down, where you experience 500 times the amount of atmospheric pressure as you would if you were in a very shallow system. Okay, so we've got on to around 23 minutes by the looks of it now. So what I'll just wrap up with saying is this area of volcanology really brings together so many different fields of science, and that's the same for many things across the Earth and the geosciences. So today we've talked a bit about physics, we've talked a bit about chemistry, geology, planetary geology, oceanography. We've also included some biology for wildlife in there. There's all sorts that we can look at, and that's what makes these systems so interesting. And it means that no matter what background you have in science, you can actually become involved in earth sciences. I've seen so many people that have come from different directions, say from an engineering background, but they've then applied their knowledge and the skills that they've acquired in that field and applied it to the geosciences. And sometimes in volcanology, a lot of physicists do very well in volcanology, because there's a lot of modeling, there's a lot of physics involved. So what I'd just like to say to anyone, whether you're a young kid or you're in high school, you're a university student, or somebody who's just really interested by these systems, if you're interested in all of the sciences and you're not quite earth sciences, because there really is something for everyone in there. So if that sounds like it might be something for you, then check it out. Okay, so I've now hit about 25 minutes, so I will wrap this up at this point. If you have any more questions, you can follow me. Now, I'm not sure if this has been reversed for you or not, so if it has, then Volcanograd or Volcanograd, whichever one you can see. So that's my handle on Twitter and on Instagram. So if you have any questions following this, then please feel free to reach out to me or to comment in the video, and I'll address them there. So it's been really great to talk to you all today for this Earth Live lesson. Just a recap on that, Lizzie Daly is running these through her YouTube channel. There's already been one earlier today. I think there was a second one about soil science that it's uploaded or redone at some point, but there will be more tomorrow, the day after, and there's a whole range of stuff for you all to get involved in. So tune in, subscribe to Lizzie's channel, and keep up with the rest of the live lessons to really get involved in some fantastic science during this time. So I'm going to finish this for you all now. Thank you for tuning in today. As I say, please feel free to reach out with any questions